Oh, sixth period, who I like just as much as fifth period. Here we go. This is that idea. I guess I'd like to know how you came up with that, because upon direct substitution, that should be infinity over infinity, right?
Uh-huh.
All right. And so infinity over infinity to the calculus ignorant might say, well, anything over itself is 1. Okay. To which case I would ask you, what is this reduced to?
Lloyd?
That's love. It says love. Lloyd? Love. It says love. What is that reduced to? Okay. Your confusion is very much my point. Infinity. Yeah. Infinity, those are numbers. They're ideas, okay? Infinity is an idea. It's a notion. It's not a number to be played with like it's a number. It's like love. It's just an idea. It's a great idea. It's a wonderful idea, but it's not to be treated like a number. So you wouldn't reduce love over democracy, and you wouldn't reduce this to 1, because really it's an idea. Now, that said, though, you obviously knew it wasn't 1. How did you know it was infinity? More powerful? What do you mean more powerful? Faster? What do you mean faster? Grows faster. Okay, grows faster. The idea of comparing growth rates is L'Hopital. Compare growth rates. Because when we do a limit, we're really not looking at a moment in time. We're looking at what happens as this gets bigger and what happens as this gets bigger. And we compare how the two gets bigger, compare, and we reduce. So L'Hopital's rule then is to say, if you get a limit problem that results in 0 over 0, that obviously is a problem. That's not 0. It's not a number. We don't know what it is. It's indeterminate, which I'll cover in a second. It's indeterminate. Then you can go about your business by saying, well, what's the rate at which they go to 0? What's the rate at which g goes to 0? Which really means you look at or compare the limit of their derivatives as x goes to a. That's then where we get in this compare of the rates idea. Now, we will have 2 indeterminate forms. 0 over 0, it matters the rate at which they go to 0. And infinity over infinity, again, the rate at which they go to infinity matters in terms of what the overall limit goes to. Sometimes they have proportional rates, in which case you'll get a number. Sometimes the denominator will grow way faster than the numerator, in which case it would go to 0. Or sometimes the numerator will grow way faster, in which case it will go to infinity. There's all these different plays. It's the play between the two, okay? Have a nice weekend.
Thank you.
All right, so this can be used in a lot of ways, just like one-sided limits and infinity as well. But real quick vocabulary. I get people that once in a while use these 2 words interchangeably. That can't stand. Indeterminate versus undefined. Look at this from an Algebra 1 perspective. When I teach this in Algebra 1, I would say something like this. Let 0 over 0 equal something, okay? If I used rules of algebra, I can multiply 0 over, and I would get this equivalent statement. All right, so what number makes that true? 0 times what number is 0? Could it be 5? Okay. Could it be 7?
Yes.
Okay, could it be anything?
Yeah.
But can you ever really figure out, is there anywhere to go from here to figure out what it really is?
No.
Okay, we cannot determine it, indeterminate. What if, however, you had something non-zero-ish over 0 equal to x? By the same idea of algebra, multiply the 0 over. What number times 0 equals 2? There is no such number. There's no number defined that you could multiply by 0 and it would be 2. It's not defined that way. There's no number defined that way. So please don't use these interchangeably. They're very different. Indeterminate means there is an answer, I just don't know what it is yet. Undefined means there's just no answer, period. Okay? So consider this then. Let's look at a famous problem we've done before in a different angle. That sine of x over x problem is a famous limit problem that we normally did numerically with a table, right? All right, now this time with L'Hopital, you're going to look at it a different way. We say, I know that you're both going to 0, so let's talk about the rate at which they approach 0 and compare their values as we get closer and closer. Well, that means then we're going to look at their derivatives. The rate at which sine approaches anything, it says rate of change, is cosine. The rate at which x approaches anything is a common rate of 1, constant rate of 1. Therefore, comparing the rates as we get closer and closer to 0, this amounts to 1. Now that is what we got from the table, remember? And that's how L'Hopital's rule works. Is if you get this indeterminate I don't know form, rather than pick up your calculator and look at how the table starts to approach, you can look at their derivatives, and that's why it's an application of derivative chapter, and see how their derivatives approach. By the way, I'll say this in terms of, this is not a little, this is kind of a side note here, because this is, I forgot to mention this earlier. This really implies that for small x's, sine of x and x are pretty much the same. Now, did you know then that in engineering, for sine of very small angles, you can often just use as a stand-in the actual number itself? For example, if I said, what's the sine of 0.2? I'd say, oh, it's about 0.2. And if, look at it in your calculator. If you do sine of 0.2, you'll see it's doggone close to 0.2. Sine of 0.2 is 0.198. Now, surely that's only for small x's. Sine of pi is not pi. Right? We know that's not the case, right? So it's only true for when we approach 0. This is often used when you are dealing with small quantity angles. You often just use the angle itself as the sine standard. All right, back to the point at hand. Give me this next limit, sine of x over x at pi. You were taught way back when that the first thing you do when you do a limit is you try to plug it in. So if you direct substitute, what's sine of pi? 1 over pi, which is sine of 1, what? 0 over pi, which is 0, yeah? Are you with me?
Yes.
Okay, so you might be thinking, well, that doesn't seem new to me. It's not. My problem here is that once you learn L'Hopital, people love it so much that they overuse it. They use it when it is not to be used, okay? L'Hopital only works for indeterminate forms. If you try to use this derivative process when it's not appropriate to do so, you will get a wrong answer. For example, if you said, oh, I'm doing a L'Hopital chapter, I must be doing a L'Hopital problem, here we go. When you take the derivative, you get cosine of x over 1, and that limit is -1. You can see that using L'Hopital when it is not called for, when it's not indeterminate, will give you a wrong answer. You only use it when you get 0 over 0 or infinity over infinity. Only in indeterminate cases, never any other. Understood? Okay, try those 4. Let's see if you're on the right track. Feel free to talk it over with your math amigos, so we'll go over them in a couple, 3 minutes. Who is that?
James.
Hi, James. How are you?
Yeah.
Good, thank you. Bless you. Thank you. When we derive behavior, we say this is infinity because he cases that. That really means you run out the rates of change. So that's yes, so the derivative of multi-ratio derivative is one under square root of one minus only use this derivative idea when
It's not 0 over 0. Wait, no, go like that. It's the 1 over root.
How'd you go the first one?
I got it.
Good.
What about on the test? I think it's right. I mean,
What about the next one? It is 0.
yes.
Okay, that's a 0, not a 6. Okay? You agree?
Yeah.
Okay. Did you get to the third one or give you another minute?
That's
About to the third one. Okay. As x goes to 0 from the positive side, what does natural law go to?
Negative infinity.
Negative infinity. What does x go to? Positive 0. Okay, is that an indeterminate form? If I decide to divide negative 1 billion by negative 1 billion, is that, I wonder what it is. I don't know. Or is it, I know what it is. You know what it is. When you divide some huge number by a small number, you get a huge number. Okay, is it infinity or negative infinity? Negative infinity. Okay, negative huge divided by positive small is negative huge. It is not indeterminate. Do not use L'Hopital. Okay, did you get a chance to do the last one or one more minute? Let's do it. Okay, what is sines? Do you remember what? You know, sine looks like this. So what does arc sine look like? Yeah, it looks more like a helix going vertically, right? A sinusoid vertically, right? The function sine actually, arc sine actually only goes from negative pi over 2 to negative 1 to positive 1. That said, then, as x goes to 0, what does arc sine go to? 0. Whether you do that graphically, which is how I think, or whether you do that analytically, either way, the top goes to 0. Cool? The bottom goes to 0, obviously. So it is appropriate to use L'Hopital. Did you take the derivative properly? What is the derivative of inverse sine of 2x? 2 over Square root of? Okay, why is the top 2 there? Chain rule. Okay, the denominator is 1. As it goes to 0, this approaches 2. Okay. All right, those are the outcomes. Are we clear so far? Okay. Even more fun is the next problem. Okay. If you try and direct substitute, you get infinitely large over infinitely large. So is it appropriate to use L'Hopital? Yes. It is. So we use L'Hopital. What is the numerator derivative? 3 to the 3x. What is the denominator derivative? Upon direct substitution, now we get what? Didn't work? Do it again. If the original function to the original function is equal to the limit of the original derivative over the original derivative, it's also equal to the second derivative over the second derivative. So we can do it again. So next derivative is 90 to the 3x over 2. So we get infinity. Okay, with that said, would you use your noggin to maybe determine if this is L'Hopital, maybe do one case, and then maybe look for a pattern to see a final case, and then your answer. This actually is a nice primer for Calc 2 topics to come. Taylor series.
If there was a case like this on the test, would you expect anywhere?
I would expect, yes, first maybe first the indeterminate explanation. Then it's a ginger one. That is good. That is satisfactory.
Yeah.
I would love it if you could detect the pattern. Get it? So, yeah, the first case would be 3e to the 3x over 100x to the 99th, which obviously is still indeterminate. The second case would be 3 squared e to the 3x over 100 times 99 times x to the 98. So you're going to keep getting indeterminate until you take how many derivatives? 100 derivatives. What's the last one?
E to the 100, 3 to the 100.
3 to the 100th, e to the 3x over 100 factorial. When you take repeated derivatives, you get factorials. And that is part of, by gross, I'm sure you mean fun. And so your final answer then is as x goes to infinity, as powerful as 100 factorial is, and it's pretty darn powerful, it's still overcome by e to even bigger, bigger, bigger powers. So it is infinity. All right. And then try the last one, and we will move to the 18th part. We'll be done. Yes. I took another derivative. So that's where the dot, dot, dot comes down. The third would have been 100, 99, x 98, x to the 97. So you're going to keep getting infinity over infinity until you can finally get rid of that bottom. And so really that's what the dot, dot, dot was for. I would have to keep taking derivatives, 100 derivatives, before I finally got rid of my infinity over infinity problem, and it became just infinity over a constant. Does that make sense? Ready?
Over 2.
Your answer is 0.
Wait, what?
What is e to the negative infinity? 0. And over, what's negative infinity squared?
Infinity.
Positive infinity. So what's 0 or tiny approaching zero. Tiny small positives divided by huge positives is 0.
So that was not the thing.
That is not indeterminate. You should not be taking derivatives. Okay? Now, as I said, it's crucial that you show this step before you're doing L'Hopital. To drive that point home one more time, this is an AP problem on the last few years. It's been pretty common that they throw in L'Hopital in a multiple choice or a free response attempt setting. This is a part B of a free response. Try it, and I'll show up and let you think about it.
Well, they are. Oh, I was thinking about this. That would be
Ready? We can knock this out. I want you guys to have some interesting. Okay, so this is where I talked to Mrs. Law, who's a grader, and she said the way they graded this, the way I taught this last year, probably would have lost points. I stressed that you have to show this as indeterminate. And on a case like this, whatever, this doesn't require a lot of work to be shown. It's just you plugging in, okay? But this is not a no-brainer that this is 0. And so they were pretty picky about, you can't just say, hey, the top is 0 without some kind of, hey, this is why this is 0 justification. So you really would have either had to write this one of two ways. You could say, hey, I'm looking at each of these guys and what happens as x goes to 3, and done them separately, or go off to the side and say, hey, I'm really getting into the numerator, and I'm really showing you details. It's not some obvious case like this. I'm communicating my thought process. Okay, so what does that top limit approach? Why? Yeah, remember this is like an area accumulation function. Okay, it's saying how much area do you accumulate from 0 up to 3, and it's really how much signed area do you accumulate. And wouldn't you agree that you get the same positive and negative areas? So that goes to 0. Okay, that then needs to be shown either here or here, something along the lines of the limit as x goes to 3 of somewhere in there. You need to say, hey, the top is 0. The bottom, you could definitely cut some corners. I think we can all see that that's 0, so that doesn't have to be as rigorous. You with me? All right, now you've determined it's a L'Hopital case. Now you crank out your L'Hopital. So you might communicate, hey, I'm using L'Hopital, which means G prime. over 2x. And then just like, I mean, all these things are consistent. Just like in these problems, you can't just go straight from G prime to the answer. You have to connect it to F. What is G prime's connection to F? It is F. All right, and then finally, that's making all those connections and saying what we got to say. And so as x goes to 3, F goes to -3, and 2x goes to 6, and so our answer is 91. Yes. Okay, that makes sense. I'm going to practice that a little more because I guess they're pretty picky about it. Yeah.
So then you have this final word showing this sort of stuff there.
Yeah.
Okay.
I will give a couple practices to make sure you're showing it well. Okay. All right. For the few of us who are remaining, I will hit questions now on 76, 7? You still have 76? 76 questions. Finish. Those of you who are leaving, have a nice day. Please don't betray me and leave before you're supposed to. I assume you're leaving in plenty of time.
They're all lying.
I don't know. They wouldn't do that. Okay. Questions on 76 if you have them.
Pardon me, we release all high school student council members and cheerleaders, and release all fall athletes at 1:35. Thank you.
All right. 76 questions if you have them.
Number 6.
6. Okay.
Number 10.
10. All right, 6 and 10. Those sound familiar. I think those are the other class. All right, so here we go. 6 is, look at the wrong one. Okay, 6 was meant to throw you because they got you thinking in odd power of trig mode, and then in number 6 they threw at you something like this. What's the antiderivative of sine squared plus cosine squared? You had to switch gears. What is sine squared plus cosine squared?
1.
1. And so it's just, that's the expectation. It's not kind of tricky. Okay, 10. 10, you might need the answer for. Check your answer to 10. Did you know?
I have no idea what you said.
Oh, that the derivative of sine of some angle in x degrees is the cosine. It is that. Did you get that for an answer?
Like, no. After I looked.
Okay, well, yeah. Here's the deal. That's degrees, sorry. An angle in degree measures. Every trig derivative you know is dependent on being in radians. And so if I ask you what's the derivative of sine, if it's radians, it's cosine. But if it's in degrees, it's a big stinking mess. Why? If you're so inclined to stick with me for a few minutes, I know it's Friday afternoon, but imagine if I graph sine to scale in radians. Then that means I'm going to make one unit about this big. And if I graph sine to scale in radians, then 1 pi over 2 would be about 1.57. It would be about here. 3 or pi would be about here. And I'd get this kind of thing, yeah? Stick with me and I'll get you there. If I did this on graph paper and I graphed a tangent slope here, and I counted boxes, I would actually see that the slope there is exactly 1. So that if I graph the derivative at 0, the slope is 1. And if I at pi over 2 graph the slope, it would be 0. And so the derivative graph is cosine when I graph in radians, because the scale is this 1-to-1 box kind of thing. But if you graph in degrees, then consider what this graph would look like if drawn to scale in degrees. I wouldn't get to that top of the sinusoid until 90 degrees, which would be in the hallway over there, or Miss LeBlanc's room there, which would mean the slope would actually be so slow growing, it would look like that, or even less. So if I were to draw the slope in degrees at that point, that tangent slope would not be 1. That tangent slope would be something tiny, like about 1/60th if I counted boxes. So you would see then that the graph of the derivative in radians would be more like something really small that wouldn't even look cosine-y. It would be something so funky and stretched it wouldn't look familiar. That idea of degrees being so huge in numbers, 90, and the ratio being 1 versus radians where the numbers are pretty much the same is the difference between the two. If I take the derivative of sine when it's in degrees, it's not cosine. It's cosine shape, but it's totally stretched and flattened out in this terrible way where the amplitude is tiny and the period is huge. That's the idea. Now, how I got there is to say, I don't know how to do the derivative of sine in degrees. So I'll do the derivative of sine in radians, and I convert it to radians. What's the conversion rate from degrees to radians? I over 180. Pi radians to 180 degrees. Now at that point, that's taking the derivative of sine in radians. If I took the derivative in radians, it would employ the chain rule then. It would be cosine of pi x over 180 times pi over 180. That's what I got.
So like, I'm kind of like, so I was like not processing that it was x degrees. I was like thinking of it as like a variable, like that was constant. But so like, how did you go from x degrees to straight up x? Is it still x degrees?
It's still this. No, the degrees canceled. Once I multiplied, I can, so the degrees are goners. And so really this is radians here. Remember when you express angles and there's nothing shown, it's assumed radians. Okay? Okay. Let's go to, that was 10. Anything else on 76? 20. And Anamika, yes?
18. You just did.
Okay. 20 and 18. 76, 20, and 18. 20. Oh, yeah. 20 is a bit of a... Oh, no, I was thinking of something else. Okay.
It's nice.
For 20... X squared y 0 and 5x plus 2y. Okay, you're supposed to show that the tangents at the origin are perpendicular. So surely tangents implies it means the derivative at the origin. And perpendicular means opposite reciprocal slope. So I need to take the derivatives, find the derivatives at the origin, and hopefully there will be opposite reciprocal slopes. Does that get you started, or shall I continue?
Yeah, got there and then I'm still.
Okay, so what was your derivative here? dy dx was what? Do you have it somewhere you can see what's going on?
Oh,
or
no, just kidding.
All right, let me know if you have trouble getting there. But I think the slopes, this derivative at the origin was negative 5 over 2, or 5 over 2, or 2 over 5. I remember there being some 5s and 2s in there. And I don't want to bail you out and do it for you. So if you are on the right track, you understand what I'm asking you to do, then I'll have you do it rather than me do it for you. if you understand what I'm talking about and it still doesn't come out, let me know. 18. What shall we go over it or no?
Yes.
Okay. Integrate x e to the 2x plus, okay. This goes to integration technique and making small distinctions between u sub and integration by parts. And really, the first thing is, I thought, well, should I take out a, oops, sorry, that would be doing the question, that's not the question, x e to the x squared. I thought, would it pay off to factor out a greatest common factor and all that stuff? And I think the intention is that you integrate each part of the sum separately, which in sums you surely may do, not products or quotients, but in sums you can split that up and look at those separately. Now, this is a product where one is not the derivative of the other. So I would say, oh, so maybe integration by parts. This is a product where you're kind of getting a chain rule derivative, and one is the derivative of the other. This must have been a chain rule. When you see a chain rule result, it's u sub. So there's your two big techniques that we've learned. U sub's the more important of the one, too, but they're both pretty good. So you're going to approach this with integration by parts in that regard.
DV would be
dv, yes. U is x and dv is e to the 2x, and make sure that when you integrate, you get a half for the balancing or whatnot. Okay? That should get you going. Yes, sir.
Just for integration by parts, if they're balanced,
Oh,
do you
yes.
still plug that into the u, or would you plug it into the...
You do the antiderivative and so you don't change the limits.
So you wouldn't change them?
You don't change the limits on integration by parts. You kind of say, so this kind of stuff off to the side is great, but there's no extra component where you say, hey, when x is this, use that. You just integrate, because when you integrate, everything's still x-ish, you don't actually go to using these in your answers. And so because this is x in your antiderivative, then to use x values is appropriate. Yeah. Okay? Yes?
we have two different constants.
You can just, you technically could call it 2, and I had a weird professor who wanted to see C1, C2, and let C equal C1 plus 2. That's ridiculous. Just one constant. Okay? That's good. Questions on 77, if we could get one or two knocked out.
Number 4.
4,
17.
17,
23B.
23B,
19C.
19C. Don't you love it when they throw those multiple parts at you? I think. All right, number 4, 77, number 4. 4 was that the trough problem. So where did you, so this is the picture, it looks like this, 5 is the slant, 15 is the height, I think it was 2D, looks like that, yeah? Where did you put your origin? Please tell me you put it at the bottom.
Yes.
Yay. Okay, bottom. 1, 2, it's 2 full. My problem then was right away when you start into the work, whatever row is, you can work that out. The distance requires you to know the top of the container because you're pumping to the top of the container now, yeah? And you don't have it. But this is where your geometry skills come in handy. You know this is a right triangle and it's isosceles. So through that you get 5 over root 2. This has got to be a 45, 45, 90 over here. 5 over root 2 for the height and 5 over root 2 for the max. 5 over root 2 for the max x. So what's the distance then? 5 over root 2 minus y. The volume, that's the volume of these sheets of fluid. Each sheet has a different distance, so we do it in sum all the different work to pump all those sheets out. So what is the width of those sheets? constant x or 2x? 2x. The length is 15 and the height is dy. Okay? The limits of integration will be 0 to 5 over root 2 or just 0 to 2? Do we need to pump out up here or do we just pump out up to 2? I mean, okay. Now this is accumulating where we pump out sheets. This is an accumulation of the work to pump out each sheet. So this is saying from where to where do I get sheets of water? 0 to 2. Okay. It's only where you're doing the work do you have to accumulate the force. The only other thing then is the x relationship. What's the relationship from y to x? 5 over root 2 over 5 over root 2. This is a 45, 45, 90. So what are the sides here? They're the same. So the rise and run are the same. The slope is 1. Okay, so y equals x, and therefore you can just erase that x and put in a y. Cool? Okay. Athletes, do you need to go? I don't want to make you. You don't have to. You could run down there. You're an athlete. 17. 17 is a good one. It tells about this region between 1 and 4. And it says at some point this curve has a maximum value of 4. And at some point this curve has a minimum value of -6. You see? And you can look at the multiple choice questions and they ask you, what do you know about the area under the curve from 1 to 4? Now, don't worry about the multiple choices yet. I'm going to give you some work and you're going to see the choice is easy. Wouldn't the integral be at its greatest if the function was at its maximum value as long as possible and maybe at the very last minute it turned down to hit that low value? In which case the integral would be upper bound by, it couldn't be any more than that rectangle. What's the rectangle's area?
16.
It's from 1 to 4, so not 0 to 4. So 3 by 4, the max, it could not be any more than 12 because the y value never went above 4, so the area could never go above 12. On the low end, say the curve was almost always at the low end of -6, and maybe at the very last minute it turned up. And actually it couldn't even equal 12 because it had to go down at some point. The low end then, what's the lower bound? What's the least that could be? No, it goes down to -6, sorry. -18, and must be greater than -18. Now, with that, it's easy to see what choice. A is the integral has to be greater than 0. Does it have to be greater than 0? Well, no, the curve could be down here, so it doesn't have to be greater than 0. B is, does the curve have to be less than 20? Well, yeah, we said it has to be less than 12, so does it also have to be less than 20? Yes, it does. C is, does it have to equal 16? That's ridiculous.
After the bell until the band passes by the room. Thank you.
And then D is, does that have to be negative? That's definitely not the case also. I don't know if it's positive a lot of the time or negative a lot of the time. So the answer is B. Okay? Because 12 is less than 20. And therefore the integral is less than 20. Cool. I think that's going to be it. The other class didn't get 277, so if you don't turn it in, it's okay. But I definitely should get 76. Have a super weekend. Have lots of fun. And down with your bad selves. Don't forget the fingers. Okay? Use that. But give me credits. Always cite your sources.
Right.
Really, Miss Rick? Right here.
I put that, and then when I do what they go on,
Maybe it's not. Is it water?
Well, yes.
So that's 6. So let's see, 30 times 2. So 30 times 6, that should be 180. I think it's 200.
Oh, Carlos gets out. He's outie. Look at all y'all.
Oh, I forgot to pause this. Is that right?
No, it's still recording.